Chapter 18 of the Romance of Modern Photography. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Photography by Charles R. Gibson. Some interesting achievements. The largest photograph in the world. How it was developed. Enlarging photographs. An amusing incident. A gigantic camera. The photographer inside the camera. Telephotography. Good pictures taken from a distance of 1 mile. Nature photography. Ballooning and photography. Photographing the New York subway. Calculating exactly when a photograph was taken. Faked photographs. While America is the country of big things, Germany can boast of having produced the largest photograph in the world. The accompanying illustrations, see frontispiece, show how this gigantic photograph was handled. In the larger illustration, we see the great photograph mounted on a large wheel or drum, having a circumference of 41 feet. A number of very large tanks had to be constructed so that the gigantic print might be developed, cleared, fixed, and washed. These tanks were so heavy that it was necessary to have them on wheels and to construct a miniature railway track, along which they might be moved as desired. The washing tank required to be 50 feet in length, 6.5 feet wide, and 2.5 feet deep. Where is the dark room to hold such enormous developing baths, etc.? The only way out of the difficulty was to develop the photograph in the open air during the night. Some idea of the magnitude of the task may be gathered from the fact that more than 10,000 cubic feet of water was used in washing the print. The subject of the photograph was the Bay of Naples. The complete panoramic picture measured about 40 feet by 5 feet. It is evident that no camera could hold a plate or film of such a size. The method of obtaining the photograph was as follows. First of all, 6 panoramic views were taken. Each of these measured 10.5 inches by 8 inches. These 6 photographs contained the whole detail of the final picture. Joined together, they would form a miniature of the gigantic photograph. From each of these 6 photographs, an enlargement was made. The process of enlarging is well known, but will be explained a little later. Each enlargement measured about 6.5 feet long by 5 feet, and to obtain these, it was necessary to have a very large lens, measuring 1 foot in diameter. While these enlargements were made separately, they were not made on separate sheets of paper. One long sensitized paper, the complete foundation of the final picture, was prepared. Then an enlargement of the first negative was made directly upon this paper. Next to that, a similar enlargement of the second negative, and so on, until the whole 6 enlargements had been made in succession. This must have been a difficult task, for the picture is not seen upon the paper until the complete bromide print is developed later. How very ingeniously this difficulty was overcome was shown by the final result. It was practically impossible to detect the boundary line of any 2 plates. Then came the task of developing the hidden or latent image of the complete photograph. From the illustration, it will be seen that 12 men were required to look after the developing of this one great photograph. The man on the top of the ladder is projecting iced acetic acid from a hand pump onto a part of the photograph which is already sufficiently developed. The action of this acid being to stop development. At other parts of the photograph where the image was faint, it was found necessary to force the developing by applying an energetic developer by means of sponges. In the smaller illustration below, the print is being unreeled from the developing wheel into the clearing bath, and this illustration will probably give the reader a better impression of the length of the photograph. Our large number of basketed jars containing the different chemicals will be seen at the side of the developing wheel, large quantities being required to fill the different tanks. Altogether, the production of so large a photograph is remarkable. It is possible that some readers may not be familiar with the process of enlarging. The method is very simple. It will be evident that if one were to use a negative as a magic lantern slide, one could project an image onto a white sheet, instead of throwing the image onto an ordinary lantern sheet. Let us replace the insensitive sheet by a large piece of sensitized photographic paper. All the variety of light and shade will be faithfully recorded by the photographic paper. We might use ordinary printing out paper if the source of light we were using was good strong daylight, and provided we could depend on a sufficiently constant light. In Great Britain, however, it is usual to employ a bromide emulsion paper, which is very much more sensitive to light, and with which an artificial source of light may be used. It has already been noted that the image upon the bromide paper is invisible until it is chemically developed. If the photographer, using bromide paper, desires to use daylight, he darkens his room by means of a shutter or cloth screen, leaving only a small window into which the back of his camera will tightly fit. He now uses his camera as a daylight magic lantern. He places the negative of which he desires an enlargement in the back of the camera, just where the ordinary photographic plate goes. The daylight enters the camera through this negative, and an image is projected into the darkroom. He focuses this image upon a piece of paper, and when it is sharp, he replaces the paper screen by a sheet of bromide paper. After a suitable exposure, the bromide paper is developed, and a record of the enlarged image is secured. When it is desired to enlarge pictures by means of artificial light, then a special projecting apparatus is used, this being simply a specially constructed magic lantern. It is an interesting fact that a negative film may be enlarged directly by chemical means. The negative is first of all placed in a bath of ammonia, and in about 2 hours the film is freed from its glass support. The film then distends, the process being hastened if necessary by the addition of a little hot water. The enlarged film is then floated onto a large glass plate and allowed to dry. It is obvious that the whole limit of enlarging by this process cannot be very great, probably not more than twice the size of an ordinary negative. Then again, in the event of any accident, the original negative is lost. This distension of the negative film reminds me of an amusing incident which happened quite accidentally. A photograph had been taken of some friends, and in the amateur's haste to get the negative dry enough to print from, he placed it near a fire. The negative film distended, but only in one direction, and the resulting prints were very comical. Every person was so short and stout. The effect was exactly that seen in a curved mirror, such as is sometimes used at exhibitions for affording amusement. I believe Glasgow can boast of having possessed the largest camera in the world. Many years ago, the late John Kibble, who erected the handsome greenhouses, known as the Kibble Palace, in the Botanic Gardens of Glasgow, was the possessor of an immense camera. It was mounted on wheels and drawn by a horse, the whole arrangement being in appearance rather like a furniture removal van. This camera was used in the days of wet collodion plates, so that it was necessary to prepare the plates immediately before taking the photographs, and then develop the plate immediately afterwards. Where are the plates to be prepared and developed? Inside the camera itself. It is curious to think of the photographer and his assistant being both closeted inside the camera while a photograph was being taken. First of all, the glass plate had to be coated with the sensitized chemicals, in the method described earlier under Scott Archer's name. Then the picture had to be focused on a white screen in order to find the exact position in which to place the photographic plate. While the plate was being exposed, the photographer and his assistant had to keep clear of the projected image. Then, when it was deemed that the plate had been sufficiently exposed, the plate was straightway developed. Some excellent photographs were taken by this gigantic camera in the busy streets of Glasgow. It is indeed remarkable that it was possible to take instantaneous photographs with so large a camera. An elderly gentleman, who was a contemporary of Kibble, tells me that he was inside this huge camera on several occasions, and the arrangements for preparing and developing the plates were most ingenious. Facing page 284, we have an illustration of telephotography. The upper illustration is a photograph of St. Albans Abbey taken from a distance of 1 mile. The picture of the abbey itself is necessarily very small, and one cannot see much detail. The lower illustration is a photograph taken from exactly the same position, 1 mile distant, but this has been taken through a telephoto lens. In this picture, one sees the abbey very distinctly. It is difficult to realize that the trees, so clearly seen in the foreground, were nearly 1 mile away from the camera. The little square marked off in the upper illustration shows exactly how much of that photograph is contained in the lower illustration. Telephotography is practically photography through a telescope, the telephoto lens acting as the telescope. There are decided advantages in the telephoto lens. It admits far more light than a telescope would do, and it is so constructed that its focus does not require a long extension of the camera. There are many useful applications of telephoto lenses. We shall see one great use of these in the chapter on photographing the stars. Telephoto lenses have also been of much service in photographing the architecture of inaccessible parts of a building and mountain scenery. Another interesting application is in photographing birds in the air or in their nests. One great advantage in natural history work is that the photographer can obtain a near view without going close up to the animal and possibly disturbing it. In connection with nature photography, the two brothers Kearton, England, have done a great deal of most interesting work. Their photographs of birds and nests are well known through their lectures and writings. In looking at the illustrations which they have published from time to time, one sees the great advantage of getting actual photographs of birds upon their nests, etc. It would be an interesting occupation to compare many artist drawings of birds with the actual photographs now obtained. Our present interest, however, lies in the taking of the photographs. It is quite evident that the Keartons are enthusiasts. They relate that in their photographic expeditions, they have slept for nights together in empty houses and old ruins, descended beetling cliffs, swum to isolated rocks, waded rivers and bogs, climbed lofty trees, lain in wet heather for hours at a stretch, tramped many weary miles in the dark, spent nights in the open air on lonely islands and solitary moors, endured the pangs of hunger and thirst and the torturing stings of insects, waited for days and days together for a single picture, and been merely drowned, both figuratively and literally. This enthusiasm was born in these photographers, for one of them tells how when he was only 9 years of age, he went out nest hunting, and coming upon a nest which was new to him, he determined to wait till the bird returned. Hiding himself in the hedge, the little fellow waited patiently, but the bird was long in coming. Darkness fell, and sleep soon overtook the young enthusiast. It was only when his people became alarmed at his continued absence, and a search party had been sent out, that the boy was aroused from sleep. While the Kirtans are most desirous that amateur photographers should betake themselves to the fields, they very wisely point out that such photographs as they themselves have obtained are not to be got without a great deal of patience. In order to let the would-be photographer know what he must be willing to endure, one of them says, "Kneel in one position for half an hour and look steadfastly through the keyhole of a door. Multiply the time and pain by 11, and add a complete disappointment when some idea will be gained of what has been happened to my brother and myself over and over again during the last few years." The Kirtans devised many means of getting their camera close up to the nests. One plan was to have the camera enclosed inside a stuffed sheep, with the lens peeping out through a hole in the breast. The operator then hid in a rush-covered tent, whence he could watch for the bird's return, and pulled the trigger from his hiding place. At other times, the photographer concealed himself and his camera inside an imitation ox, taking the photographs through a hole in the breast of the stuffed animal. Another prominent nature photographer, in quite a different field, is Herr C.G. Schillings of Germany. It was indeed a bold idea to photograph wild animals in perfect freedom. Imagine any man going right among the big wild game of equatorial East Africa and calmly taking their photographs. Professor Lambert of Stuttgart has referred to Schilling's photographs in the following terms. "These pictures are of the greatest importance. In them, the wild animals of Africa will live on long after they have been sacrificed to the needs of advancing civilization." Some of Schilling's most remarkable photographs were obtained during the night by means of a flashlight, and owing to this fact he has entitled his work "With Flashlight and Rifle." On one occasion, he photographed 3 full-grown lionesses as they came down to a pool to drink during the night. Imagine a man lying in wait in the dark midnight, hoping some savage beast would come close enough to him to be photographed. In another photograph, a lioness is seen actually springing upon an ox, while a large lion, having allowed the lioness, as is his custom, to make the attack, comes to help to devour the prey. In one photograph, a lioness was taken at a distance of only 3 yards. On many occasions, while Herr Schillings was following some other animal, such as a gazelle, he suddenly found lions and lionesses within 100 paces, stealthily approaching him. One can scarcely imagine the nerve power required to keep cool under such circumstances. Among Herr Schilling's sitters, there were huge elephants, rhinoceroses, hippopotamuses, giraffes, zebras, hyenas, etc. These photographs of animals in perfect freedom at their own home were not obtained without much experience gained through many disappointments in previous expeditions made by Herr Schillings. This gentleman has the rare combination of being an expert photographer and a fearless hunter. Some interesting photographs have been taken from balloons, and it is a strange fact that some of the best photographs have been obtained on dismal rainy days. The reason why moisture in the air aids aerial photography is doubtless because it prevents the dust motes from reflecting the sunlight. It is quite impossible to take a photograph from a balloon at a height of 4,000 feet because of this reflection from the dust motes. One well-known aeronaut, the late Reverend James Bacon, received a very strange request from the Russian government. It was shortly after the tragic incident in the North Sea, on which occasion a British fishing fleet was fired upon by some Russian battleships which were proceeding to the seat of the Russo-Japanese War. The Russians declared that some Japanese torpedo boats had been seen among the fishing boats, and they were naturally anxious to prove that this was the case, if they possibly could. The Russian embassy requested the British aeronaut to proceed to the scene of the mishap in his balloon, and while hovering over the waters, to take photographs which would show the depths beneath. The idea was to photograph the phantom torpedo boat which the Russians declared they had sunk. Although it is quite possible to take good snapshots from a balloon of the regions below the sea level to a considerable depth, it is needless to say the aeronaut did not accept the commission. When one of the biograph companies undertook to take animated pictures in the New York subway, they took on hand a very difficult task. It is apparent that the light must be very good if one is to take about 1,000 photographs in each minute. It would have seemed to the ordinary photographer to be a practical impossibility to produce sufficient light in the underground tunnel to enable such photographs to be taken. The American photographers thought differently. They fitted a large railway truck with hundreds of very powerful electric lamps. They used what are known as mercury vapor lamps. These give forth a rather hideous light, the red rays being absent. This, however, is a splendid photographic light. The total light produced was equivalent to 54,000 candle power. It would require between 3,000 and 4,000 ordinary glow lamps to produce this candle power, and even then the total light would be very weak photographically when compared with the truckload of mercury vapor lamps. The photographs were taken from a moving train, which practically chased one of the regular trains through the tunnel. The powerful light was carried by the second train, and the light was thrown immediately ahead so as to light up the rear of the regular train. The resulting pictures showed the train flying through the tunnel and then drawing up at one of the stations. Here, some passengers were seen alighting, while others entrained. Then off went the train once more. The pictures attracted considerable attention because of the gigantic lighting scheme, which was necessary. If someone were to hand you the photograph of a building and ask you to calculate the exact position from which the picture had been taken, you might not be willing to undertake the task, but the request would appeal to you as being quite a reasonable problem. If, however, someone were to hand you a similar photograph and ask you to calculate the day and hour when the photograph was taken, you would doubtless consider the request as a jest. This seemingly impossible task was undertaken some years ago by a mathematician. The subject was a photograph of one of the American observatories in Nebraska. This photograph was found in one of the old catalogs of the observatory, but it was not known when, nor by whom, the photograph had been taken. Professor Riggs set himself the task of calculating the exact date and hour at which the photograph had been taken. Fortunately, the sunlight had been strong, so that the shadows cast by different parts of the buildings were very marked. By means of these shadows, the mathematician was able to calculate the exact position of the sun in the heavens. This was no light task, but as the sun has a twofold motion, as each motion is independent of each other, a shadow gives us both the time of the day and the day of the year. Having obtained the exact position of the sun, the professor found that there were two different dates during the year on which the sun was in this particular position. One day was the 2nd of May, and the hour a few minutes past 3 o'clock in the afternoon. The other possible date was in the month of August. A close examination of the grass and the trees in the photograph decided that the earlier date was the correct one. Having calculated the exact hour and the day of the year upon which the photograph was taken, how could the particular year be determined? The shadows would be the same each year at the same time, so some other evidence must be appealed to. As the photograph appeared in the observatory catalog for the year 1894, it was clear that the picture had been taken before that date, but it might have been taken many years earlier. How then could the particular year be discovered? It so happened that the weather vane of the observatory was distinctly seen in the photograph, and its direction was due northwest. A continuous record of the direction of the wind is kept in the observatory, so it was an easy matter to find out in which year the wind was due northwest at 3 o'clock on the 2nd of May. It was found that the wind had been due northwest on that day and hour in 1893. Further evidence could be brought forward by the photograph. Some trees at a distance of 3 miles were very distinctly seen, and this fact indicated a particularly clear atmosphere. Therefore, the barometer must have been high, and the wind must have been steady for several hours. All these conditions exactly agreed with the records for the 2nd of May, 1893, while an examination of the records for the same day in 1894, 1892, 1891, 1890, etc., shows that in none of these years did the necessary conditions prevail. It was therefore definitely proved that the photograph had been taken at 3 p.m. on the 2nd of May, 1893, the achievement being quite worthy of Sherlock Holmes. In order to show that the day and hour were correct, a duplicate photograph was taken in the following summer at 3 p.m. on May 2nd, when every shadow was found to coincide exactly with those in the original photograph. While a simple photograph is a truthful witness, it is apparent that it is a witness which may be easily tampered with. If a photograph could be used as a witness in a law court, then a criminal might be able to prove an alibi by trickery. It is quite an easy matter to insert one's photograph into a second photograph and then reproduce it as a complete picture. A criminal might have his photograph inserted into some picture, which it could be proved was taken in a distant town on the day and at the hour of the alleged crime. The criminal could not have been at the place of the crime, as the photograph would prove him to have been in a distant town. When an heir to the Crown Prince of Germany was born, there immediately appeared a picture postcard with a photograph of the Kaiser with his little grandson in his arms, while the Crown Prince and Princess stood close beside him. The photograph appeared within 24 hours of the birth of the future ruler, and before the Kaiser, who was in Norway, had ever seen his little grandson. This faked photograph was the subject of an action at law, brought by a photographer who did photograph the royal group later. Quite a lot of legitimate amusement may be got by faking photographs. A man may be shown sitting at a table earnestly playing cards with himself as his opponent. Or again, quite a natural photograph may be produced of the man having a heated discussion with himself. Faked photographs occasionally appear in our law courts, and it has been repeatedly proved that to issue a faked photograph as genuine is distinctly illegal. End of Chapter 18.
Chapter 19 of the Romance of Modern Photography. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Prajakta. The Romance of Modern Photography by Charles R. Gibson. Photographing the stars. Early daguerreotypes of the moon, the astronomer's camera, a difficulty overcome, some useful applications of photography, photographing stars never seen by man, photographing an extinct star, discovery of small planets, photographic discovery of Saturn's ninth satellite, going round the wrong way, wonderful maps of the moon, vast nebulae that dwarf the solar system, photography and solar eclipses, photography and the spectroscope, how we tell what the stars are made of, some stars approaching us, discovery of a double star, an amusing incident on the Alps, photography's important part in astronomy. Photography was in its very infancy when it was suggested to try and obtain pictures of the heavenly body. The first photographic studios were just being opened, 1840, when Dr. Draper of New York succeeded in taking the moon's photograph by the daguerreotype process. These early attempts were very imperfect, but some fair specimens of lunar photographs were shown at the Great London Exhibition of 1851. These were also taken by an American. The first idea was simply to use a telescope as the lens of a camera, and this method continued up till 1870. Why not use an ordinary camera? We may easily obtain a photograph of the full moon in an ordinary camera, but the image will be very small, probably about 1/10th part of an inch. To obtain a larger image, we must use a lens having a greater magnifying power. Suppose then that we have a camera fitted with a special telephoto lens and we try to take a photograph of the full moon. We find that our efforts have met with success, and so we decide to try and photograph some of the distant stars. This time we meet with complete failure, and we find the reason of our failure to be that the stars will not stay in one place long enough to let us get a photograph. As a matter of fact, it is our camera that will not remain in one position. It and we with it are all moving through space. With our faithful moon, we are waltzing around the sun. It is the turning motion which bothers us when we try to take a photograph of the heavens. We did not notice this when we took a photograph of the full moon because the light was so bright that we practically took a snapshot of it. The exposure was only a fraction of a second. We find, however, that so very little light reaches us from some stars that these either waves of light require several hours of constant action upon the chemicals on the photographic plate before they can make any impression. Herein lies our difficulty. For during these hours, the camera has been turned round in the waltz to quite a different position. Indeed, it has never remained long enough in one position to receive any impression of the star which we were endeavoring to photograph. How then are we to overcome this difficulty? We must keep turning our camera round in the opposite direction to that in which the earth is carrying it, so that the eye of the camera will remain steadily fixed upon the star. Of course, it appears to us as if the stars were moving and we ourselves were stationary, for we have no sensation of movement through space. Everything, including our atmosphere, is going with us, and no resistance is offered to our progress. The large telescopes had already been fitted with clockwork, which kept them moving round at the required speed to counterbalance our movement in the great celestial vaults. The camera could therefore be clamped onto the side of the telescope so that it too would keep a star in view. A star appears as a mere point of light so that any movement will be very noticeable. Even the best clockwork may not serve to keep the camera quite steadily on the star for a very long exposure. In this case, the observer must watch the star through a small telescope which is moving along with the camera. This telescope is provided with cross wires in the eyepiece so that the observer may get the star into a definite position as regards these cross lines. And if the clockwork tends to take the camera too fast or too slow, he may retard or hasten the clockwork to rectify the amount of such error. In this way, excellent photographs have been taken. It will be of most interest to the reader to know what useful purposes photography has served in the study of the celestial bodies. We are accustomed to hear stars described as of the first magnitude or the sixth magnitude and so on. This is really no description of their relative sizes. It refers to their apparent size. One star might appear larger than another because it happened to be nearer to us. Even the sun and the moon appear to us to be very much the same size, and yet we know that the diameter of the sun is 400 times greater than that of the moon. Again, one star might appear larger than another because it had greater luminosity. We see that the magnitude really tells us nothing but the apparent size of one star compared with another. But astronomers have found it convenient to describe the stars in this comparative manner. Stars of the first to the sixth magnitudes are visible to the unaided vision. Those of the seventh magnitude and upwards can only be seen with the aid of telescopes and may therefore be called telescopic stars. As more powerful telescopes were made, further ranges of stars were brought to view till the number of magnitudes was increased to 20. It is obvious that a question of the personal equation comes in here, for one observer might describe a certain star as belonging to the 10th magnitude, while another observer might say that it should belong to the 11th magnitude, and so on. Photography can supply a more reliable comparison. If we expose a photographic plate to a group of stars for 5 seconds, only the brightest stars will be able to impress their images upon the sensitive plate. A second and similar plate exposed for 10 seconds will reveal some of lesser brilliancy as well as those already seen upon the first plate. A third plate exposed for 20 seconds will reveal more, and so on. If we go on increasing the time of exposure in this manner until we are into hours instead of seconds, we shall find that after we have photographed all the stars visible in the best telescopes, we may still continue adding to the numbers on the photographic plate. We are then photographing stars which have never been seen by mortal man. Astronomers have reason to believe that some of these stars which we have just been considering are so very far distant from us that the ether waves of light sent out by them take many thousands of years to reach us. This seems almost incredible when one considers the fact that light travels at the enormous speed of nearly 200,000 miles per second. Here is a curious thought. We might set up a camera today and take a photograph of stars which ceased to send forth light before the flood. Indeed, it may be that we have photographed stars which disappeared before man ever lived upon this earth. It would not affect this statement even if we granted that man may have been a tenant of this planet for 100,000 years. The largest possible number of stars to be seen by the unaided vision certainly does not exceed 5,000. In one part of the heavens, as many as 200,000 stars have been carefully mapped out with the aid of powerful telescopes. In the same area, as many as 2 million stars have been detected by photography. Picture the astronomer of not so long ago sitting night after night at his telescope, hard at work making a map of a certain part of the heavens. What a tedious and difficult task to fill in all these little specks in their proper places. Then picture the present day astronomer setting his camera in any desired position and in a few hours obtaining an absolutely true chart. Photography accomplishes in a few hours a task which would otherwise require years of patient labor. The astronomer is keen to note any change among the heavenly bodies, and so he repeatedly compares the heavens with previous charts. When an additional star like object does appear, he watches it carefully for hours to see whether it is a fixed star or a small planet known as an asteroid. If he finds that it has any forward motion, then he knows that it is an asteroid. Nowadays, photography is a useful assistant in determining this point. On the negative, all fixed stars will appear as little dots, while the small planet will appear as a streak, for it will have made a slow procession across a part of the plate. It will be remembered that the motion we have given to the camera by clockwork merely keeps the camera pointing steadily at the stars, so that any movement of the small planet among the stars will be detected. The physical nature of these asteroids is not known, but it is supposed by some astronomers that they may be fragments of some great planet disintegrated in past ages. The largest of these small planets is about 500 miles in diameter or roughly 1500 miles in circumference. It would be little more than a whole day and night journey to go round one of these asteroids in a non-stop express train. Other asteroids are very much smaller and may not exceed 50 miles in diameter. Since photography has been called in to assist, there have been some 30 new asteroids discovered every year. As many as 3 of these small planets have been discovered on one photographic plate. The present total is between 5 and 600, and it is believed that we have now photographed all the asteroids whose diameters exceed 50 miles. Like all other planets, these asteroids are lighted by the Sun and are comparatively near to us, while the stars, which are themselves suns, are millions of times farther off. While we think of those asteroids as very small bodies compared with the great planets, we must not picture them as being of merely meteoric size. Many of them are about the size of Great Britain, and they move around the Sun in the space between the 4 inner planets and the 4 outer or giant planets. A century ago, we believed that only 3 of the planets had satellites, faithful attendants like our moon. Now we know of 5 such systems, and it was photography that discovered 2 of the new satellites for us. There is an interesting point in connection with the discovery of one of these 2 satellites. In 1898, it was announced that a new satellite, Phoebe, had been discovered moving around Saturn. This made the ninth satellite for the mysteriously ringed planet, but the announced discovery was not generally accepted as fact. The only evidence was a photographic plate. There must have been some mistake. All attempts to find this satellite with the best telescopes failed. The beautiful and youthful Phoebe must be a myth, like the great Apollo himself, from one of whose epithets the word Phoebe had been coined. Long before this time, one observer believed that he had discovered another planet, to which he gave the name Vulcan, but this supposed discovery was never confirmed, although many photographic plates were exposed to that part of the heavens in which Vulcan should have been. The supposed discovery was therefore determined to be an error. When the announcement of Phoebe's discovery was made and astronomers could not find the satellite with their telescopes, one astronomer jokingly suggested that Phoebe had gone off to look for Vulcan. Years went past and nothing more was heard of Phoebe, till an astronomer in another quarter also found this satellite of Saturn upon a photographic plate. If some amateur astronomer had suggested that the reason why Phoebe could not be caught by the astronomer's telescope was that the satellite was moving around Saturn in the opposite direction to all other satellites, it would no doubt have caused amusement in scientific circles. Such an idea would certainly seem absurd, and yet this very strange fact has actually been discovered by astronomers. Phoebe moves around Saturn in a retrograde direction. Ultimately, the satellite was caught by the telescope, but its luminosity is so feeble that there are probably only 3 or 4 telescopes existing powerful enough to detect it. Excellent photographs have been taken of the moon. At first, it was usual to photograph the whole moon, but better results have been obtained by taking larger photographs of different parts of our satellite. Recent photographs seem to indicate that the moon is not yet quite dead, that there is still volcanic activity. One eminent astronomer believes that there is vegetation on the moon. By measuring the shadows cast by the mountains of the moon, it has been possible to calculate the height of these mountains, some of which appear to be covered with snow. Imagine making a complete map of a body which is distant 238,000 miles from us. Yet, the maps of the moon which photography has enabled us to make certain every hill or valley that is 1 mile long and half a mile across. We can only photograph one side of the moon, for she never turns round to let us see what the other side is like. The moon therefore performs a true waltz with our Earth around the Sun. Our Earth, on the other hand, keeps continually turning around on its own account during the volts. Another important part played by photography in our study of the heavenly bodies has been in connection with the Sun, and more especially at times when our faithful moon has come between us and the Sun, producing a total solar eclipse. The red flames or prominences seen during a total eclipse were proved to be appendages of the Sun, for successive photographs showed the moon covering and uncovering these in her grand march past the Sun. An idea had also existed that the beautiful corona seen around the disk of the moon at the time of total solar eclipse was an atmospheric effect. But two photographs of the corona taken almost simultaneously from two places many hundreds of miles distant from one another proved conclusively that the corona had no connection with any interference of our atmosphere, but was an effect occurring at the sun. Photography has been of great service to astronomers in studying the nebulae, which had previously been a puzzle. These nebulae look like far distant clouds or dull patches of light, and indeed were sometimes liable to be mistaken for comets. Photography discovered vast nebulae which had never been detected by the most powerful telescopes. These nebulae have turned out to be great masses of incandescent gas. It has been impossible to say how far these vast bodies are distant from the Earth, but there is evidence that they are at least as far off as the stars. Our whole solar system is a mere speck in the universe when compared with a great nebula. Each of these vast masses of incandescent gas may, in ages to come, be transformed into a star. We believe that every star commenced as a nebula. Who can say, but some day, when our present photographs of nebulae become ancient records, the astronomers of ages to come may be able to point to these old charts as proof of the birth of some star known to them. The nebula in our photograph being the embryo or beginning of their star. When we consider our Earth to be a mere speck compared with the Sun, and when we think of the whole solar system as a mere dot compared with a great nebula, we become lost in wonderment. When we think of all the activity upon this earth, and when we consider the exquisite design in the tiny microscopic shells, we find it very difficult to place our whole world within a mere dot in the universe. It is none the less true that if some of the neighboring planets were inhabited by intelligent beings, their astronomers would fail to discover our world with the best of telescopes. Indeed, unless it so happened that these inhabitants of another planet had acquired the art of photography and applied it to astronomy, they would never know of the presence of our planet in the universe. Perhaps the most interesting application of photography to astronomy is in connection with the spectroscope. While we find many of the sciences correlated, one would have thought that astronomy and chemistry must forever stand apart. We cannot hope to get to the stars to find out their chemical composition, but the spectroscope has enabled us to find out the different elements present in the sun and other stars. In those earlier chapters, which dealt with the subject of color photography, we considered the effect produced by passing light through a triangular glass prism. We saw that white light was analyzed or split up into a spectrum of beautiful colors, commencing with red at one end and finishing with violet at the other end. In order to make the resulting spectrum as sharp and defined as possible, the light is passed through a narrow slot before it reaches the prism. In this way, the overlapping of the bands of different colors is prevented, and we have what is called a pure spectrum. A simple spectroscope is therefore merely a glass prism and a shutter with a slot in it. Sometimes the shutter is mounted in a brass tube and an arrangement made whereby the width of the slot may be altered at will. Then comes the glass prism, and another brass tube with an eyepiece, which is practically a small telescope to magnify the image of the spectrum. If our subject was the spectroscope and not photography, we should want several chapters to deal with the subject. We must content ourselves with a few details, such as are necessary to a proper understanding of the part photography plays in connection with spectroscopy. Before we can examine any substance by means of the spectroscope, the substance under examination must be sending out light. The sun and the stars are therefore suitable objects for examination. But how are we to know what the different spectra mean? Suppose we make a few simple experiments in the laboratory before attempting to photograph the spectra of the different stars. We wish to examine a piece of iron by the spectroscope. We must make it white hot. On looking at it through the spectroscope, we see a simple continuous spectrum such as is got from white light. We try another solid body and the result is just the same. Indeed, we find that all solid or liquid bodies, when made to incandesce, give us a simple continuous spectrum. How then are we going to learn anything from the spectroscope? First, let us see what appearance a burning or incandescent gas has in the spectroscope. We burn a piece of sodium in a hot flame, say that of a Bunsen burner. We at once see a very bright line in the yellow band of the spectrum. This bright yellow line always appears in that position when sodium is in the form of an incandescent gas. Hydrogen, when incandescent, gives a bright line in the red and bright line in the blue. There are other lines seen with good apparatus, but these two lines are always particularly prominent. And so, we find that every incandescent gas has definite bright lines. Suppose we are examining a sodium flame and we see in the spectroscope a bright line in the yellow. While we are looking at this, someone makes a white light shine through the flame by placing a white hot solid body behind it. We immediately see a dark line in the yellow band in the place of a former bright line. The sodium flame has absorbed certain rays from the white light passing through it and so cut them off, leaving a blank in their place in the resulting spectrum. We may therefore detect sodium by this dark line. This is what we have to do when examining the spectra of the heavenly bodies. The light from the distant star is passed through a spectroscope and a record of the spectrum is made to impress itself upon a photographic plate. We find a great number of dark lines. The positions of these are carefully noted and compared with the different spectra which we can produce in the laboratory in the manner already indicated. A careful examination of a photograph of the spectrum of the sun shows us that hydrogen, sodium, iron, copper, nickel, zinc, etc. all exist in that great body which is 93 millions of miles distant from us. We are not to think of copper mines, etc. in the sun. What the spectroscope shows is that all these substances exist in the sun in a gaseous state. Today, many observatories are taking photographic records of the spectra of the different heavenly bodies. These records should be of great interest in the centuries to come. Future astronomers may compare our records with the spectra then obtainable and thus note any alteration in the condition of the stars. Even in our own time, many interesting facts have been discovered by very carefully comparing the lines obtained in different photographs of the spectra of some distant stars. The lines of hydrogen, for instance, should appear in all photographs in exactly the same position in the spectrum, no matter whether it be a distant star or a laboratory experiment which is being photographed. It was found, however, that there was a slight difference in the position of these lines in certain stars. Take for instance the star Sirius, the brightest in the heavens. and perhaps better known to some as the dog star. It was found that the lines representing hydrogen were very slightly nearer the red end of the spectrum than on the records made of other stars and also of hydrogen birthing in the laboratory. What could this mean? Have you ever been standing on a wayside railway platform when an express train was about to run through the station? The whistle of the engine seems to rise in pitch as the train rushes towards you and falls again to a lower note as the train passes away. Indeed, it has quite the effect of a siren, and yet we know that the whistle is sounding only one definite note. The whistle is setting up one definite rate of air vibration all the time. But as the train rushes towards you, these air waves arrive one after the other quicker than they would if the engine was standing in one position, hence a higher pitch of note. Imagine the whistle giving a definite number of blows to the atmosphere in a certain space of time. We then picture the sound wave set up by the first blow to be traveling towards us, but the engine darts forward as it gives the second blow. It is just as though the engine made up very slightly upon the first sound wave before it dealt the second blow, so that the air waves follow each other closer than they would otherwise do. They come tumbling against your ear in quicker succession than they would do if the engine remained standing while it dealt out the blows. On the other hand, when the engine is rushing away from you, the vibrations or pulses are a little farther apart, the engine moving farther and farther away at each blow. Keeping this analogy before us, we note that the position of the dark lines really indicates the pitch of the different rays of light. If the rate of vibration be increased, the dark line will move nearer the violet end of the spectrum, that is, up the scale. If the rate of vibration be decreased, the line will move down the scale towards the red or lower end of the spectrum. Looking at the record of Sirius, we find the displacement is so small that it requires delicate apparatus to measure it. The displacement is towards the red end. The dog star is therefore receding from us. The amount of displacement in the spectrum indicates the rate at which this far distant star is traveling. In the case of Sirius, we find it is moving away from us about 20 miles every second. Other stars are receding at rates of from 10 to 30 miles per second. One might be rather alarmed to learn that the spectrum photographs of some stars prove that they are approaching us at somewhat similar speeds. It will be apparent that there is no cause for panic when we consider that the nearest star to us is many billions of miles away, while some stars are distant thousands of billions of miles from our little globe. It is surely a very remarkable achievement to be able to tell whether a body distant billions of miles from us is approaching or receding from our Earth. Why, if one stands on a long straight road, it is difficult to tell whether a distant tramway car is approaching or receding from us? There is another interesting astronomical discovery due to photography which I shall merely mention. Many spectrum photographs had been taken of one of the stars in the constellation known as the Great Bear. On some of these photographs, it was found that one of the prominent lines in the spectrum was sometimes double, while in other photographs it was single. It was proved that this star must in reality be two separate bodies very close to each other. Photography therefore discovered the double star, which up till then passed itself off as a single star to all observers. The line was single in some photographs because at the time of taking such photographs, the one star revolving round the other hid its twin brother from the eye of the camera. There is an amusing incident related by Sir William Abney in connection with spectrum photography. On one occasion, this learned scientist was taking some photographs of the sun's spectrum from the summit of one of the Swiss Alps. He had traveled from England to get a clear atmosphere and also to get a little nearer to the sun by climbing a high mountain. Of course, the actual difference in distance would make no appreciable difference, but by climbing to this height, he would have less atmosphere between the sun and his camera lens, which would be a distinct advantage. The particular object of study was to determine whether a certain group of lines in the photographic spectrum beyond the visible part might not be due to a hydrocarbon vapor. While Sir William Abney was arranging his instruments, an American gentleman came upon the scene and watched the scientist with patient interest. After 1 hour of silent watching, the American said, "I guess, sir, you have got a photograph behind that." To this, the scientist agreed. The American next exclaimed, "Well, sir, what are you doing with the sun?" It flashed into the mind of the scientist that here was an opportunity of having some fun. Sodium, of which soda is one combination, had already been found in the spectrum of the sun. Alcohol and brandy might be classed as carbohydrates along with the hydrocarbon vapor for which he was searching. With these thoughts in his mind, the scientist gravely replied, "Sir, we have already found soda in the sun, and now I am trying to find the brandy." The American made no further remark. He hurried down to Zermatt and informed the people in the hotel that he had encountered a lunatic Englishman on the mountain. The poor fellow was trying to get a brandy and soda from the sun. In closing this chapter, it may be of interest to add that one observatory, Harvard College, has taken as many as 6,000 stellar photographs in 1 year. This indicates the important part which photography plays in connection with modern astronomy. End of chapter 19.
Chapter 20 of The Romance of Modern Photography. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Photography by Charles R. Gibson. Photography and Science. To speak of photographing sound waves in the air will doubtless seem quite ridiculous to the ordinary reader, and yet several scientists have accomplished this wonderful feat. I remember seeing quite a large collection of photographs of air disturbances which were taken by H. Stanley Allen at Lord Blythewood's laboratory in 1901. The method of taking these photographs was very ingenious, and the results were admirable from a scientific point of view, although the man in the street would have failed to see their value. There was nothing picturesque about them. The general reader would appreciate more readily the photographs taken by Professor C.V. Boys, where airwaves are distinctly seen around flying bullets. A collection of these photographs is to be found in the Physics Department of the South Kensington Museum, London. The general effect in a photograph of a flying bullet is very much the same as that of a steamer plowing its way through the sea. Both the waves which spread out from the bow and the disturbance or wake which follows in the trail of the steamer are well represented in some photographs of a simple flying bullet. In other photographs, the airwaves are seen reflected from a sheet of metal placed in their path, and their behavior is exactly like waves in water. But how did Professor Boys manage to photograph flying bullets? To attempt to photograph a flying bullet by means of the very best of instantaneous shutters would be absolutely useless. We may take a snapshot of a train going at an express speed of 60 miles per hour, but the bullet is traveling at a speed of 1,400 miles per hour. A momentary flare of flashlight powder is good enough to obtain a picture of a crowd of people assembled together, but quite useless in the case of a flying bullet. During the sudden flash of light, the bullet would have passed with lightning speed across the area covered by the photographic plate. It is obvious that the illumination must be very short indeed before we can catch the image of a flying bullet. It goes so fast that we are unable to see it in its flight. Where are we to get an illumination sudden enough for the purpose? An electric spark will give an illumination of the shortest possible duration. It has been calculated that some electric sparks occupy less than the 1/1,000,000th of a second. But all electric sparks are not of the same duration. Indeed, Professor Boyes found that the first kind of electric sparks which he tried were far too slow to photograph the bullet shot from a magazine rifle. During the fraction of a second in which the spark existed, the bullet had traveled half an inch across his photographic plate. By adjusting the electric apparatus, he was able to get sparks of so short duration that the flying bullets appeared in the photographs as though they were quite stationary in mid-air. But how is the photographer to snap his picture at the right moment? He wishes to have the image of the bullet right on the center of his photographic plate, but the whole time during which the bullet is within the compass of his camera cannot exceed the 1/200th part of a second. It is quite evident that the photographer cannot press the button at the required moment. The bullet itself must operate the electric spark. We need not trouble with the detail of the electrical apparatus further than to note how the spark is timed. A spark gap is arranged in such a manner that a spark occurring at this point will illuminate the whole area covered by the camera. An electric charge is waiting ready to spark across this gap, but it cannot do so because of another small gap in one of the connecting wires. The moment that this second gap is bridged over by a piece of metal, the discharge takes place, causing a spark at the desired point. Let the bullet itself be the piece of metal to bridge the gap in the connecting wire. This wire gap may be arranged so that it forms the bullseye to be aimed at. The instant that the bullet fills this gap, the electric discharge takes place across the illuminating spark gap, and this all happens so very suddenly that a good snapshot photograph is obtained of the flying bullet. An interesting series of such photographs was taken of a bullet piercing a sheet of plate glass. A photograph of the bullet was taken just entering the glass, and this showed a cloud of glass dust thrown backwards in the opposite direction to that in which the bullet was traveling. Another photograph of the bullet was taken after it had reached a distance of 5 inches beyond the sheet of glass. This showed the bullet completely enveloped in a thick cluster of glass dust, giving the bullet the appearance of a long brush, the 5-inch space between the bullet and the hole in the plate glass being also filled with a mass of glass dust. Another photograph which Professor Boyes took when the missile had reached a distance of 15 inches beyond the glass showed the bullet quite clear of the glass dust, but close to the bullet there was a single piece of glass, which, no doubt, was the piece immediately struck and punched out by the bullet. This piece of glass is seen to be traveling along by itself at a speed practically equal to that of the bullet. This small piece of glass is seen to be causing air waves on its own account. The air waves in all these photographs might be mistaken by a casual observer for cracks on the negative. These experiments ingeniously carried out by Professor Boyes were suggested by some similar experiments made by Professor E. Mach of Prague. The method of obtaining the photographs was considerably modified by Professor Boyes. Professor Boyes also took some interesting electric spark photographs of a fine column of water falling from a jet. At first, the water looked like a rope or cylinder, and then it began to bulge out at intervals, leaving a narrow neck between each pair of beads. At last, these beads were seen to separate into little drops, quite separate from one another. The same scientists photographed 2 drops of water in the act of bouncing against one another. The drops were flattened as they met, and behaved just as though they were India rubber balls. Professor Worthington took a series of electric spark photographs of a drop of water falling into milk. One photograph was taken just as the drop of water struck the surface of the milk, and this showed quite a cavity in the surface. Then one of the succeeding photographs showed quite a tall pillar of milk in the place where an instant before there was a hole. This effect was caused by the milk rushing in to fill the cavity, and in so doing the high pillar was momentarily formed. But for the testimony of the photographic plate, we could not know that this strange result really happened during the splash of a drop of water. Lord Rayleigh took some very interesting electric spark photographs of a soap bubble in the act of breaking. In these photographs, the retreating edge of the bubble, as it broke, is seen with all the accuracy and sharpness of a stationary object. Some interesting facts concerning ripples on the surface of liquids were determined by Dr. J. H. Vincent by means of electric spark photography. This scientist caused different sets of ripples to be set up simultaneously on the surface of Mercury by means of 2 points attached to vibrating tuning forks. The electric spark photographs showed many interesting phenomena which could not be seen by the eye owing to the rapidity with which they occurred. Some of the phenomena met with in the study of sound and light, such as reflection, interference, and refraction, have been well illustrated by this means. Some of these ripple photographs may be seen in the physics department of the South Kensington Museum, London. I have already referred in an earlier chapter to the electric spark photographs taken of a flying insect. It is interesting to note that another experimenter made a series of such photographs of a cat falling from a height. The idea was to show how a cat was able to turn round in the air and land on her feet upon the ground. I understand that from a pictorial point of view, the photographs were not very successful, the reason being given that the subjects did not care for this form of scientific investigation. No doubt the experimenter would have difficulty in obtaining sufficient illumination to get all the detail of a falling cat. In the illustrations facing page 298, we have 2 very interesting photographs of wave effects taken by Dr. Vaughan Cornish. The upper illustration shows 2 waves crossing each other almost at right angles and each continuing on its own way. Dr. Cornish has kindly given me the following particulars. Quote, "The intention of the photograph is to illustrate a fundamental property of waves, namely, their interpenetration and subsequent continuance, each in its original course. It required 6 months waiting to obtain it. The photograph was taken with a No. 1 binocular camera pointed downwards, the center of the picture being about 12 feet distant. The photographer stood in the water, which had a depth of only 2 or 3 inches, upon a sandy shoal. The occasion was low water of a spring tide, and the locality the sandy shore opposite Branksome Shine, near Bournemouth, England. The weather was calm, and the ordinary waves, coming in from the offing and breaking some distance out, gave rise to small solitary waves, foaming at the front. At first, the solitary wave leaves the foam behind, but as the water becomes shallower and the speed of the wave is thereby reduced, the foam which it makes travels with it and becomes a roll of opaque white froth, which outlines the wave front with great distinctness and gives the photographer his opportunity. At the moment when this photograph was taken, a solitary wave, deflected from the shore and traveling seawards over the sandy shoal, met the next incoming wave at a spot which was brought to the center of the camera's field of view. Below this, in the photograph, the waves had previously met and passed through each other, each pursuing its original course. The line of momentary interference is recorded by an irregular band of foam. On either side of this, the waves are seen to be pursuing each its original course. The increased amplitude of the momentarily combined wave is clearly shown at the point of intersection." Unquote. I may remark that this photograph attracted a good deal of attention at the St. Louis Exhibition, USA, and it was one of the photographs selected by the Royal Commission for the souvenir volume of the British exhibit. Footnote: the binocular camera mentioned by Dr. Cornish in connection with this photograph of crossing waves is rather like an opera glass in appearance. One half of the instrument is a camera, and the other half is practically one eyepiece of an opera glass. The photographer holds the instrument up to his eyes as he would hold an opera glass, and this he does while he is in the act of taking the instantaneous photograph. In this way, the photographer was able to bring the image of the crossing waves fairly onto the center of his sensitive film. End of footnote. The lower illustration, page 298, is a photograph taken in the Dyfi Estuary, North Wales, and shows sand waves produced by currents. This photograph is of scientific value, and by request, Dr. Vaughan Cornish has given a copy of it for preservation at the Geographical Society of Berlin. The full title given to the photograph is, quote, "Current Mark and Tidal Sand Waves," unquote. When considering nature's camera, I incidentally remarked that the eye of a particular species of beetle produced as many as 25,000 images of the object which it was viewing. The experimental proof of this is very difficult to carry out. It is indeed remarkable that anyone can dissect the head of a beetle so as to remove the eye without injury. The retina and the dark pigment interlining the eye have to be very carefully removed with a fine camel hair brush, and the miniature transparent lens has to be placed in proper position in front of the objective of a powerful microscope. Having got the tiny lens, the microscope, and the camera in position, the scientist then takes a glass transparency, say a photograph of a man, and he places this so that a strong image of it is reflected onto the tiny lens, or in other words, the eye of the beetle. The microscope enlarges the manifold image formed by the insect's eye, and a photograph is taken of the enlarged image produced by the microscope. It will be obvious that it would be quite impossible to observe the manifold image produced by the beetle's eye except with a microscope, as the whole area of the eye is a mere speck, and in this space there are 25,000 distinct images. Of course, one cannot hope to make the whole of these images simultaneously visible in one photomicrograph, the necessary magnification being so great that only a portion of the whole can be brought within the microscope lens at one time. In a photomicrograph measuring 1 3/4 inches by 2 1/2 inches, I have counted as many as 100 distinct images, each image being an exact duplicate of the other. An Austrian professor, anxious to see what an insect really sees, arranged his apparatus in a similar manner to that just described, but instead of throwing the image of a photograph upon the insect's eye, he allowed an image of the view obtained from his window to fall directly on the little lens. In this experiment, the eye of a firefly was used so that a larger picture might be produced, not by any increase in the size of the tiny eye, but because this insect's eye does not produce manifold images, as in the previous case. Quite a good photograph of the window with a church in the distance was obtained by this means. With such very small lenses as those from the eye of a beetle or a firefly, it is necessary to take the photographs through a microscope, but experiments have been made with some of nature's larger lenses, allowing the microscope to be dispensed with. The crystalline lens taken from the eye of a freshly killed bullock has been used in place of the ordinary camera lens. Very great care is required in handling this natural lens, but the results obtained in some cases have been excellent. A totally different series of experiments was made by Professor Wood, USA, and described by him in the Philosophical Magazine of August 1906, under the title of Fish-Eye Views. In the illustrations opposite page 254, we saw how light was bent in passing from the air into water. Imagine the penny in these photographs to be the eye of a fish which is swimming in the basin. It is obvious that the fish would have a very wide range of vision, the light being bent over the top of the basin at every point around its circumference. Therefore, a fish placed at the center of a small pond of clear water must have a very wide view of the objects surrounding the pond. It is difficult to make personal experiments. Our eyes are not adapted to distinct vision under water. It is well known, however, that if one looks upwards from beneath still water, one sees the sky compressed into a comparatively small circle of light, the center of which is always immediately above the observer. It just looks as if the whole pond were covered with a dark roof, with a circular window in its center. As already stated, it is difficult to distinguish any objects that are out of the water. It occurred to Professor Wood that an excellent notion of how we appear to the fishes could be obtained by immersing a camera in water and photographing the circle of light above it. The apparatus was constructed out of a lard pail and a short focus lens provided with a diaphragm having a very small aperture in it. The lens and its diaphragm were fitted into a metal disc, which rested on a metal rim soldered around the inside of the pail, about midway between the bottom and the mouth of the pail. The lower half of the pail was therefore to act as the camera, or imitation fish's eye. This part of the pail was filled with clear water after the photographic plate had been placed in position on the bottom of the pail. This operation was necessarily performed in a dark room. Then the upper part of the pail was also filled with water, so that this part of the pail represented a miniature pond. The lens of the submerged camera was covered with a metal cap, keeping the dark chamber light-proof. This shutter was provided with a handle on the outside of the pail, enabling the shutter to be opened and closed at will. This miniature pond with its submerged camera was then placed upon the ground, and a number of extremely interesting photographs were obtained with this device. A number of men standing around the miniature pond were seen in the photograph in a somewhat distorted condition, and this must be the idea a fish gets of us when we look into the small pond or river in which he is swimming. By modifying the apparatus so it could be held in a horizontal position, one could make the camera look along instead of upwards. In this position, the camera takes the place of the eye of a fish, looking out through the glass sides of an aquarium. Some very curious photographs were taken in this manner. Again, the fish has a very wide range of view. If a straight row of 9 men were to stand close up to the side of a glass aquarium, the fish would see the whole row of them, but not in a straight line. They would appear to be standing in a large semicircle with their backs to the center of the circle. The men at the ends of the row would appear to be away out about the center of the room instead of being in a straight line with the fish's domain. It will be understood that Professor Wood was not experimenting with the eye of a fish, but with a photographic apparatus made to imitate the fish's eye. In the experiments described immediately before these, the actual eyes of beetles, etc., were used to focus the images for the camera. Photography is of great service to science quite apart from the pictorial aspect. The movements of a spot of light may record themselves upon a photographic paper, and by keeping a sensitized paper ribbon in regular processional motion, a spot of light falling upon it will leave a continuous record of all its movements. One interesting application of this fact is in automatically recording far distant earthquakes. It may seem quite ridiculous to attempt to record the altogether imperceptible tremors caused in Great Britain by earthquakes occurring in India, Siberia, or Japan. We are totally unconscious of any such tremors, but our photographic paper will inform us of their occurrence. In the British Observatory, we dig a deep pit until we get down 20 or 30 feet below the surface. We then erect a solid pier or pillar of masonry upon this deep foundation. The top of this pier pops up in the observatory through a hole in the floor and is used as a small table upon which the earthquake apparatus or seismograph stands. This instrument is therefore quite safe from all local surface disturbances. The instrument consists of a long boom, which is so very light and so delicately poised that it will move with the very slightest tremor of the earth. This boom, which is made of aluminium, will merely oscillate from left to right, the total distance of its to and fro vibration being very small. It must be obvious that there is no use in attempting to record the movements of this boom by attaching a pen or other marker to it. Any such arrangement would immediately arrest the movement of the boom. It is here that photography steps in to aid the scientist. The end of the boom carries a very light plate or shutter of aluminium, in the center of which is a longitudinal slot, while there is above this a lateral slot in the mahogany case which encloses the apparatus. The light of a lamp passing through the intersection of these slots causes a spot of light to fall upon the ribbon of photographic paper, which is kept in continuous and regular motion by clockwork. When the boom is at rest, the spot of light makes a black line along the center of the paper ribbon, while some light gets past the edges of the shutter and makes a black border on either edge of the ribbon. The very slightest movement of the earth causes the boom to vibrate, thus making the center line wavy and the outer lines irregular, as shown in the accompanying illustration, Figure D. This is a reproduction of a photographic record taken in the Coates Observatory at Paisley, Scotland, and the earthquake which directly moved the instrument occurred in far distant Shamakha, Russia. While the photographic record shows the hour and the duration of the earthquake, it cannot give any indication of the part of the world in which the disturbance has occurred. The earthquake may be recorded here several days previous to any information reaching us as to its whereabouts, especially if the disturbance is in some out-of-the-world place, where all means of telegraphic communication may have broken down. In those observatories where magnetic observations are taken, it used to be a very laborious task to note the variations in the directions of the Earth's magnetism. A large magnet, measuring about 2 feet in length, if suspended by a long silk thread, will not point steadily to the magnetic north pole of the Earth all day long. It will move, slightly to the west between 8 o'clock in the morning and 2 o'clock in the afternoon, and then slowly return eastwards. During the night there is practically no movement, as the total movement from west to east is only about the 30th part of an inch at the end of a magnet measuring 2 feet. It is obvious that it will not concern the mariner. There is, however, a scientific interest attached to these small variations, which are irregular. During some years, the average amount of movement is double that of other years. It is always greater in summer than in winter. The reading of the exact position of the long magnet was a tedious and a delicate task, which had to be performed 12 times every day. Photography stepped in and relieved the observer of his arduous duty. A small mirror attached to the magnet reflects a beam of light directed upon it, and thus throws a spot of light upon a photographic paper. This band of sensitized paper is moved by clockwork, just as in the earthquake apparatus, so that it keeps a continuous record, marked off in hours, of the position of the magnet. The observer therefore obtains a photographic chart showing exactly how far the magnet has wandered from the magnetic North Pole. The photographic spot of light serves the scientist in very many different ways, but the 2 cases just described will give the reader an idea of this kind of work. 2 Austrian inventors have used a spot of light to write down telegraph messages in ordinary writing upon a sheet of photographic paper. The one great advantage is that the pencil of light may be made to move very rapidly, so that an extraordinarily high speed has been attained. The spot of light is reflected by a little mirror, the movements of which are controlled by the electric current. The spot of light dances about on the sensitized paper, reminding one of the fairy light Tinker Bell in J.M. Barrie's Peter Pan. All the photographic records of the movements of a spot of light are made upon a bromide emulsion paper, and therefore the record is not visible until the paper is chemically developed. In the case of this high-speed telegraph, the apparatus automatically develops the record, so that the telegram is complete when taken from the machine. In the lower illustration facing page 308, we see the photograph of an apparent dark flash of lightning, and in the legend beneath this illustration, I have asked the question, is there such a thing as dark lightning? Scientists could not definitively answer this question at one time, but Dr. W.J.S. Lockyer of the Solar Physics Observatory London has helped to make matters quite clear. It has been suggested by one writer that the apparent dark flash was produced in the following way. A bright flash having occurred and made an impression upon the photographic plate, another flash follows sufficiently near to the first to illuminate the plate, whereupon the first image will appear dark instead of bright when the plate is developed. Dr. Lockyer secured photographs of quite a variety of dark flashes of lightning, and he then proceeded to imitate the results by means of electric discharges in the laboratory. If we look carefully at the dark flash in the photograph, we shall see that there is a bright core along the center of the dark flash. Dr. Lockyer was able to produce the same effect by means of electric sparks in the laboratory. His experiments quite confirmed the suggested theory of the dark flashes being due to a second illumination of the plate. Taking first of all a photograph of a single spark, he developed the plate and found that it represented a bright flash. Repeating the experiment, but leaving the sensitive plate still in the camera, he moved his sparking apparatus very slightly, so that the image of a second spark would fall clear of the first impression. He then caused 2 sparks to pass in succession, and again 4 sparks on another part of the plate. The first and second sparks were found to be dark flashes with bright cores, just like the dark lightning in our illustration. The last spark alone appeared as a bright flash. By varying the intensity of the sparks and that of the illuminated background, it was found possible to produce any combination of bright and dark flashes. It is therefore quite clear that there is no such thing as dark lightning in nature. Every lightning discharge, if photographed and immediately protected from a second flash, will show a bright flash upon development. The dark flash is only seen upon a photographic plate which has been illuminated after the first impression was made. The apparent dark flash is therefore due to some chemical action which takes place in the photographic film. Immediately above the photograph of the dark lightning is a beautiful photograph of a cumulus cloud. Cloud photographs are taken for 2 quite different purposes. The object in this case has been to show the formation of the cloud. It is most interesting to have a series of photographs of a cloud taken at intervals of 1 minute between each successive picture. In this way, one can see exactly how the cloud changes from one shape to another, totally different formation. The second object in cloud photography is to secure cloud negatives which may be used along with other photographs. For instance, one may have a good landscape photograph, but the sky has nothing of interest in it. If one prints in some clouds from a suitable negative, the general effect of the landscape is greatly enhanced. We have already seen in some of the other chapters many ways in which photography aids the scientist, not only in the study of the invisible part of the spectrum and other invisible rays, such as those emitted by radium and other radioactive bodies, but also in a study of bacteria and other objects far below the range of vision. In another chapter, we saw how photography aided the astronomer, and so on. With what has been added in this chapter, it must be clear that photography plays a very important part in scientific research. End of Chapter 20.
Chapter 21 of the Romance of Modern Photography. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by prajak. The Romance of Modern Photography by Charles R. Gibson. A camera without a lens. The pinhole camera, the disadvantages of lensless photography, why we use lenses in the camera, the making of photographic lenses, some curious points about lenses, wherein the expense lies, lenses for different purposes, what determines the focus of a lens, early suggestion of a portrait lens, how the lens bends the rays of light, is the obtaining of a good lens a matter of chance, how the form of lens is first determined. After the reader has examined the illustrations shown facing page 316, and when he learns that these beautiful pictures were taken through a simple pinhole, he may be inclined to ask why we should bother about using a lens at all. It is certainly remarkable that such excellent results may be obtained with no apparatus other than a dark box with a pinhole aperture in it. It will be obvious, however, that there must be some advantages to be gained by the use of lenses, otherwise the photographer would not pay anything from a guinea to 150 guineas for a good lens. Let us first of all see wherein lie the disadvantages of a camera without a lens. We cannot say anything against lack of definition in the two illustrations, but if we were to photograph some large object from a short distance, we should then find a want of sharpness about the picture. Before we could have a pinhole that would focus with perfect sharpness, the hole would require to be so small that it would allow only one ray of light from each point of the object to enter the camera, and the material in which this ideally small hole is to be made must have no thickness whatever. Neither of these conditions can be fulfilled, but by drilling a very small hole in a sheet of very thin brass or tin foil, very beautiful pictures may be produced. This fact is admirably borne out by the two photographs reproduced in the illustration. These photographs were taken by Reverend J. B. Thompson of Greenock, who is an authority on the subject of pinhole photography. I think that as far as landscapes are concerned, no one will find fault with the productions of lensless photography. Indeed, a lens sometimes produces an unreal effect in a photograph by giving too good a focus. In other words, the lens of a camera may bring the rays of light to a sharper focus than the crystalline lenses of our eyes do in ordinary vision. In modern photographic exhibitions, one sees many pictures which have been taken with the lenses purposely out of focus in order to produce a more realistic effect. One is not surprised to learn that it would be quite impossible to focus the pinhole picture upon a ground glass focusing screen. There is so very little light admitted to the camera that one cannot see the image. Fortunately, there is no need of any focusing. No matter at what distance one places the photographic film from the pinhole, the image is always in focus. Of course, the farther away one places the sensitized film, the larger will the image be. There is another interesting point about pinhole photography, and this is a point in its favor. The definition of the picture is equally good for all objects, no matter at what distance they are away. This sentence may seem somewhat to contradict an earlier statement in which I said that if one had a pinhole photograph of a large object taken from a short distance, one would see that there was a want of sharpness about the picture. There is really no contradiction. We do not notice the lack of definition in the distant landscape, but we should observe it in a large image of some detailed object. This evenness of definition for all distances is practically perfect in lensless photography, while it is otherwise with lenses. Both the foreground and the background are often far out of focus. Wherein then does the real disadvantage in lensless photography lie? The answer to this question must be obvious, for if one thinks of the total amount of light which can enter the camera through a pinhole, it must be clear that a very long exposure will be necessary to enable the faint image to affect the chemicals upon the photographic film. There is no use in attempting to increase the size of the hole. We should certainly admit more light, but the resulting image would be blurred. Indeed, if we made the hole large enough to admit a good light, we should find that no image at all would appear. How long then does a pinhole exposure require to be? A fair idea of the exposure required may be gathered from the general statement that a pinhole photograph requires as many minutes as it would take seconds by an ordinary camera with a lens. Accordingly, a picture which could be taken by an ordinary camera in 1 minute would require an hour's exposure with a pinhole camera under the same conditions. The chief purpose of a lens, therefore, is to admit more light into the camera and still bring the image to a focus. The old-time Italian philosopher Battista Porta found that the pictures in his camera obscura were greatly improved when he placed a lens at the hole in his shutter. It will be obvious that the more light a lens can pass into a camera, the better will it be for instantaneous photography. Hence, we hear of rapid or instantaneous lenses. As we are not considering the subject from a practical standpoint, we need not trouble ourselves with the particular forms of lenses required for different purposes. It will be of more general interest to form some idea of the method of making photographic lenses. It goes without saying that the lenses are made of glass, although there have been such things as liquid lenses. We all appreciate the light transmitting qualities of glass, and none of us would care to return to the 14th century open lattices or windows of oiled paper. Most of us have some idea of the manner in which glass is made. Certain raw materials are mixed together and practically boiled in hot furnaces. Indeed, the whole process is not unlike the making of toffee, in which the ingredients at certain stages require to be stirred with a ladle. If the raw materials used are compounds of sand, potash, and lead, then the resultant mixture is termed flint glass. If, on the other hand, the mixture is sand, soda, and lime, it is known as crown glass. Both flint and crown glass are used in the making of photographic lenses. A demand for finer work produced modifications of these. The new kinds of glass were first made in some works at Jena in Germany, so that they are known as Jena glasses. These glasses are made by adding other ingredients such as phosphorus, aluminium, etc. to the mixtures which are to be boiled. One interesting point in the manufacture of glass is the method of obtaining a regular density throughout the mass. If the glass were more compressed in one part than another, the power of bending the rays of light would vary accordingly in different parts of the glass. The glassmaker meets with a troublesome difficulty here, for if he withdraws his glass from the furnace, the outside of the mass will cool more quickly than the inner portion. This cooling of the outside will cause a greater pressure upon the inside portion so that it will become more dense. What can the glassmaker do to obviate this serious fault? He must cool the glass very gradually by means of ovens in which he can bring the temperature very gradually down. The whole mass will then cool equally and the process is called annealing. Large discs of glass may require many weeks during which they are gradually cooled. Some of the glasses which are most suitable for photographic lenses are necessarily of a soft nature owing to their composition. They are therefore much more easily scratched than is ordinary glass, hence the care required in cleaning fine photographic lenses. It is a curious fact that these glass lenses are somewhat elastic. Indeed, if the lens maker is not very careful in mounting a fine lens in its metal socket or cell, he may spoil the focus of the lens by making the cell press too tightly upon the edge of the lens. Another curious point about some kinds of glasses is that they tarnish on exposure to air just as easily as iron rusts. When the lens maker uses this kind of glass, he must protect it from the air by enclosing it between lenses made from another glass which will not tarnish. If lenses could be cast in molds in the same way as glass ornaments, the prices would be very different from what they are. But unfortunately, this cannot be. A block of glass has to be cut and then ground down to the required shape. In grinding, the glass is rubbed against a hard metal tool or mold of the desired shape, while emery, sand, or diamond dust is placed between the surface of the glass and the tool. The glass is caused to assume gradually the shape of the tool. For simple lenses, such as are used in spectacles, and for cheap lenses, this process of grinding may be deputed to automatic machines. Photographic lenses, however, not only require skilled labor, but the making of fine lenses can only be accomplished by a certain delicacy of touch upon the part of the operator. After the lens has been ground to the desired shape, it requires to be polished to remove the marks of grinding. The polishing is very similar to the grinding process, except that rough powder is used in place of the emery and a mold or tool having a softer surface, such as cloth or wax, replaces the hard metal tool. By this means, the lens is given a lustrous black polish. An imperfect polish will scatter the light into the camera and this will be detrimental to the image. The great delicacy of the work necessary in making fine lenses may be appreciated when we learn that before the operator can measure the results he has produced in the lens, he must let the lens cool down to a perfectly even temperature. The curvature of the lens will alter with an unequal temperature. Modern photographic lenses are made up of a combination of several different lenses and are fitted together like a short telescope. As already indicated, the forms of these vary greatly according to the particular purpose for which they are intended. We find lenses described as portrait, view, rapid landscape, wide angle, telephoto, universal, etc. One point of interest is that the focus of a lens, its focal length, is not dependent alone upon the shape or curvature of the lens. The composition of the glass has a great deal to do with determining the focus. Two lenses of exactly the same form may bend the rays of light in different degrees. If the two lenses are made of different kinds of glass, the one may bring the rays to a focus at 3 inches from the lens, whereas the other's focal length may be 6 inches. There is another interesting point in connection with photographic lenses, and this was observed at a very early date in the history of photography. In the Philosophical Magazine of October 1839, there is a letter addressed to the editors by Dr. John T. Towson and entitled On the Proper Focus for the Daguerreotype. In this letter, the writer points out that lenses, as then known, did not bring the chemical rays of light to a focus at the same point as the visible or luminous rays. Therefore, when Daguerre focused his picture on the ground glass screen, he was not finding the true focus of the chief rays which affected his photographic plate. The picture would appear in good focus upon the screen, but the invisible image formed by the chemical rays would be out of focus, and the resulting picture would therefore be in the same condition. The yellow rays of light produce the greater part of the illumination, and it is well known that these yellow rays have practically nothing to do with the production of the picture, as is shown by the use of a yellow lamp in the dark room. In his letter, Dr. Towson goes on to ask how Daguerre succeeds in producing such good results, and the writer explains it in this way. He points out that Daguerre stops down his lens so that light only passes through a small portion at the center of it. In this way, only the rays which require least bending are allowed to enter the camera, or in other words, only the light which is making a fairly straight course for the photographic plate gets in. Those rays which strike the lens at a considerable angle and would therefore require to be greatly bent are not accepted, for the greater the bending which takes place, the more exaggerated will be the difference of focus between the visible and the chemical rays. The reader is not to imagine that none of the visible rays take part in the making of a photograph, but this subject will fall better within the title of the following chapter. This closing up of the greater part of the lens by Daguerre necessarily meant a long exposure, and therefore Dr. Towson proposed that a large lens might be used if it was corrected so as to bring all the rays of light to one and the same focus. The particular object in view was the possibility of taking portraits from life, so this new lens was termed a portrait lens, and it required a very short exposure as compared with Daguerre's previous achievements. Having witnessed the bending of light in the illustrations opposite page 254, I do not think that any reader will have a difficulty in understanding how it is that a glass lens bends the rays. The bending occurs when the rays pass from a medium of one density, the air, into a medium of a different density, the glass, and again as the rays leave the glass and enter the air. The bending is therefore controlled by the curvature of the lens on both sides. I have repeatedly heard amateur photographers say that it is altogether a matter of chance whether one gets a good, bad, or indifferent lens when one purchases a camera. There is a certain amount of truth in this if one refers only to cheap cameras and does not include expensive lenses. The reason for this is not far to seek. A great many defects may occur in the making of a lens, or flaws may be found in the glass only when the lens is polished and practically ready for use. The lens maker has already expended a good deal of money on this faulty lens, and he can only afford to destroy it provided he is to get a compensative price for a good one when he does make it perfect. In the case of cheap lenses, he must just do the best he can. Some are sure to be better than others. With expensive lenses, however, the case is different. He is willing to throw on one side all those wherein any fault occurs, no matter at what point in the process of manufacture the defect is detected. Very great perfection has been arrived at in the making of lenses, But it must be clear that these results cannot have been attained in any haphazard fashion, nor could they have been very well arrived at by experiment. If lenses had been plastic bodies, which could be tried first of all in one shape and then squeezed out into another form, a purely experimental method might have been possible. Although I have stated at one point that a lens is elastic, it goes without saying that the elasticity is very slight and that the lens is in no degree plastic. We have seen that the making of a lens is no simple matter, even when the operator already has the necessary tools bearing the exact formation required for the particular lens which he desires to make. The curvatures of the lenses required have all been determined by mathematical calculation, and then a tool has been made in agreement with the form worked out by the mathematician. End of chapter 21.
Chapter 22 of The Romance of Modern Photography. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Photography by Charles R. Gibson. How Light Makes the Photograph. The careful housewife, especially if she lives in the country, makes use of the direct chemical action of light, although she may not be aware of the fact. When she finds that the modern laundry has failed to make her cotton fabrics white enough, she simply passes the order on to the great bleacher, light. She places the cotton fabrics in a wet condition out of doors and, as she says, bleaches them in the open air. She really gets light to do what the chemical agencies of the laundryman have failed to do to her satisfaction. This may not appear to be a very suitable analogy for the effect of light upon a photographic paper. The former is a bleaching out process, while the latter is a coloring or darkening process. But if light can make some things white and other things black, then the difference must necessarily lie within the things which are being attacked by the light. It is obvious, therefore, that light is a force which sets up definite chemical actions, but that the particular effect produced will depend upon the nature of the substances themselves. What about the latent or invisible image upon a photographic plate? In this case, there is no visible change made by the light, but that there has been a real change effected may be demonstrated at the expense of a couple of photographic plates. Suppose that we have two similarly sensitized photographic plates, each enclosed in a dark envelope. We open one of the envelopes and take the plate out so that the daylight may fall upon it for a moment. We take care that the other plate is well protected from light. We then take the two envelopes into the darkroom and examine the plates by the light from a red or yellow lamp. Both plates look exactly alike. There is really no visible change. Each plate has a creamy white film over one side. We place the plates side by side in a developing tray filled with a certain chemical solution, and very soon we see that there is a marked difference between the two plates. One of the plates has become black all over, while the other remains unchanged. The change has taken place in the plate which was momentarily exposed to the action of light. If we now place the two developed plates in a fixing solution, we shall find the white film to clear off the plate unaffected by light, so that it becomes practically a clear sheet of glass, although there remains a transparent gelatine film. The black plate comes out of the fixing solution with practically the same appearance as it had when taken from the developing bath. Now, it is quite apparent that the two plates have had exactly the same treatment throughout, with the one exception that light was allowed to attack the one and not the other. We require no further evidence to convince us that light has a very real action. What, then, do we mean by chemical change? The question hardly calls for an answer. Almost everyone knows that in nature there are a certain number of simple or elementary substances, and that all the rest of nature is made up of combinations or compounds of two or more of these elements. But we must not think of a compound as a mere mixture. We may mix ground rice and sugar together. We have not made a compound. The rice and sugar are there just as before, and we might separate them again. Indeed, if we were to sprinkle some of the mixture into a glass of water, we should see the sugar fall quickly to the bottom of the glass, while the ground rice would float upon the surface for some time. If we think of any common chemical compound, we shall see at once how different it is from a mere mixture. We know that common table salt is a compound of sodium and chloride. Now, sodium is a soft metal, which one may cut with a knife, and which if cast upon a wet surface will catch fire. Fortunately for us, sodium behaves in a more orderly manner when it enters into partnership with chlorine. If it were otherwise, we could not drop it into our soup and place it within our moist mouths without its immediately igniting. The other partner in this combination, which is known as sodium chloride in the chemical dictionary, or as common salt in the household, is the gas chlorine, which possesses a strong suffocating odor. We might take water as another example showing how completely the elements lose their individuality while they are in partnership. We know that water is entirely composed of two gases, hydrogen and oxygen. But when we drink water, we do not drink a mixture of gases. We see then that chemical change means more than a mere addition. The chemical effect of light is not necessarily a combination or union of two or more substances. Light causes some combinations to disunite or decompose. If we wish to impress anyone with the fact that light causes certain substances to unite, we have a well-known experiment at hand. If some chlorine and hydrogen gases are mixed together in a glass globe and then exposed to light, the gases will unite in a vigorous manner, announcing their union by a considerable explosion. Fortunately, the chemical changes which occur on our photographic plates are not of such a sensational character. It will be of interest to form some idea of the way in which light makes the photograph. Our best plan will be to consider in the first place what happened on Daguerre's silvered plates. It will be remembered that the first step in Daguerre's process was to get iodine to unite with the silver coating on the surface of his copper plate. This he accomplished in a very simple manner. He heated the iodine so that some ascended in the form of vapor, and in this form it came in contact with the silver of the plate. The two substances united chemically. For our present purpose, we must be content to think of these two substances as having a natural attraction or affinity for each other, thus causing them to join in partnership. It will be obvious that the partnership is not a very permanent one, for Daguerre had to take great care to keep his prepared plate away from the gentle action of light until such time as he had it arranged in position in his dark camera. The combination must be a very unstable one when it can be so very easily upset or altered by the action of light falling upon it. This very instability gave Daguerre his chance of success. Having got his plate safely within the dark camera, Daguerre opens the lens, whereupon a light and dark image falls upon the prepared or sensitized plate. We picture a chemical commotion wherever light attacks the plate, while the original partnership still holds good at such places as lie under the dark parts of the image. An examination of the plate in the dark room would not show any visible change, and so we remembered that it was by means of an accident that Daguerre discovered that there had been a real chemical change upon his plate. I refer to the magic cupboard, in which the good fairy Mercury produced a beautiful picture upon a plate which had shown no sign of change whatever when taken from the camera. And thus it was that Daguerre discovered that by exposing the invisible image to the vapor of mercury, a visible picture was formed. But what made the picture appear? Suppose, by way of analogy, that we had an iron target in which was embedded the design of a crown made of soft clay. Matters are so arranged that the clay and the iron look exactly alike, and the whole forms a smooth, self-colored surface. If we commenced throwing handfuls of white stones at the target, we should very soon find that some of the stones were sticking to some parts of the target and not to others. We therefore take good care to strike every part of the target, and when we have done so, we shall find the design of a crown standing out distinctly upon the unaffected background of the target. The foregoing is certainly a very crude analogy, but it may be of assistance in making clear what happens when the plate with the invisible image is exposed to the vapor of mercury. The plate has been prepared by the artist's light. There is an invisible design. We bombard the plate with small particles of mercury, and these unite with that part of the surface which is being specially prepared by light. Those particles of mercury which strike the parts of the plate with which light has not meddled are simply thrown off again. These are represented in the analogy by the stones striking the iron parts of the target. In this way, Daguerre's beautiful pictures were built up. It will be observed that the parts of Daguerre's plate which were not affected by light still remained sensitive to light, the plate having been kept all this time in the dark. It was therefore necessary to wash the remaining portion of the sensitive film away. This Daguerre did by washing the plate in salt water. Turning to modern photographic plates, we find light preparing an invisible picture upon the unstable chemical surface. Then follows the developing bath, and we imagine the chemicals in the developer to be attracted by their prepared design and rejected by the unaltered portions of the chemical film. Thus, the visible image appears in the film, but we must remove the unaffected portions. This process is known as fixing, but would be more descriptively named if it were called a clearing process. The chemicals in this bath have no effect upon the developed image. They simply dissolve away the unaffected portions of the film, which if allowed to remain would darken on further exposure to light and thus destroy the picture. Leaving the production of the image upon the glass negative, we turn to the photographic print on paper. We have become familiar with the fact that light produces a visible image upon one kind of photographic paper, while it produces a latent image upon another kind of paper. The former is called a printing out paper, POP, and the active part of the sensitive coating is composed of silver chloride. The action of light is to darken the silver chloride, and so the chemical change is visible at once. Exactly what the chemical change is has not been definitely determined, but the darkened substance possesses less chlorine than it did before it was attacked by light. The color produced by this darkening process is not very pleasing, but it may be altered by washing the print in a toning bath containing a solution of chloride of gold or other metal. The print is still sensitive to light, and what really happens is that the toning solution deposits a very finely reduced powder of gold upon the darkened portions of the print. This operation is carried out in daylight because the sensitive coating is not so easily affected by light as that upon a sensitized photographic plate. After the print has had a more pleasing color produced by the toning bath, it is necessary to remove all the unaffected portions of the still sensitive coat. This is done by another chemical bath, originally salt water, but now a solution of hyposulfite of soda is used. This process, although simply a clearing process, is known as fixing the print. Having already considered the development of the latent image on the photographic plate, we need not trouble further with the similar development of the invisible image produced on bromide paper. In this case, the developed image will be a positive, as it has been printed through a negative. As the present volume does not endeavor to give any suggestions for the practice of photography, it may seem unnecessary to remark that the negatives and the prints are always well washed between each chemical bath. It is necessary to stop one chemical action before setting up another, and one does not wish to carry chemicals from one bath into another bath. In some of the earlier chapters, I've had occasion to refer to the fact that ordinary daylight contains red, orange, yellow, green, blue, indigo, violet, and a great quantity of invisible rays. This fact is well demonstrated by analyzing a beam of light through a glass prism. We have no difficulty then in testing the different part that each kind of light plays in photography. We have already seen that this spectrum, falling upon a sensitized surface, makes practically no change where the red and orange rays fall. The yellow rays are almost equally inactive, while the green rays have also very little action. Looking at the visible spectrum, we have only blue, indigo, and violet rays left, and it is these rays, more particularly the bluish violet, which attack the chemicals upon the ordinary photographic plate. It will be remembered, however, that an attack is also made by an invisible foe, for the sensitive surface is affected far beyond the violet end of the spectrum. Indeed, we have seen that it is possible to take a portrait by means of these invisible rays alone. See illustration facing page 196. We are therefore quite familiar with the fact that a large proportion of the light which makes our photographs is quite invisible, and indeed that the very rays, yellow, which give us most light, according to our estimate of luminosity, are practically of no use in photography with ordinary plates. Attempts have been made to produce a photographic plate which should be affected by all colors in similar proportions to the effects produced in vision. It is impossible to do this perfectly, but the great difference between the ordinary photographic effect and that of our vision may be very considerably reduced, so that any colored object may now be photographed without such strange results as might otherwise be produced. By way of illustration, let us take some extreme case. It may be asking too much of the reader to imagine a lady dressed in a bright yellow dress with blue trimmings upon it, but suppose we have found the required subject in a circus rider. Her photograph would represent her in a black dress with light trimmings. The photographic chemist, however, has prepared surfaces which are sensitive in certain degrees to red, orange, yellow, and green rays. Plates prepared in this way are called orthochromatic. The purpose of these orthochromatic plates is to reproduce in the photograph a true proportion of light and shade. A yellow object is to look lighter and not darker than a blue object, as is the case in ordinary photographic plates, and so on. Then again, we have plates specially prepared to be sensitive to one color in particular, and these are of great service in photographing through the color screens for the three-color process of printing. When considering invisible rays, in an earlier chapter, we found that photographic plates had even been made sensitive to the rays below the red end of the spectrum. These, however, are of scientific value alone. The chemistry of photography is a very complex subject. Much mystery still remains, and a thorough understanding of the knowledge that has been attained requires one to be familiar with chemical symbols and equations. It has only been possible in this chapter to give a very general idea of the way in which light makes a photograph. End of Chapter 22. Read by Anita Hibbard, October 4th, 2022. Chapter 23 of The Romance of Modern Photography. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Photography by Charles R. Gibson. Conclusion. Among all the wonderful things that were discovered during the fruitful 19th century, photography must ever hold a very high position. We have all become so familiar with the art that we have almost ceased to marvel at its achievements. We have no photographs of the late Queen Victoria as a girl. Even when she ascended the British throne, there were no photographers to record the coronation scene. At that very time, Daguerre in France and Fox Talbot in England were busy trying to entrap the image of the camera obscura. Now there are tens of thousands of men making photography their daily business, while a census of all the amateur photographers throughout the civilized world would make a library of very bulky volumes. If one seriously considers the fact that a whole living scene may be registered by photography in 1,000th part of a second, one cannot but be impressed with the marvelous achievement. Think what a small fraction of time a second is, and try to imagine 100th part of that. Then look at the illustration facing page 268, and consider that the whole detail of that picture was recorded in 1/500th part of a second. It is indeed difficult to realize this fact. Of all the wonders related in connection with photography, I think the phenomenon of the latent image remains the most extraordinary. We place a plate with a chemically prepared surface in a dark box. which has a small opening with a glass window formed by several pieces of curved glass. We have a dark blind over this window, but we withdraw the blind for the smallest fraction of a second. What has happened? We take the plate and examine it in a dark room by the aid of a red lamp. We see the plate exactly as it was when we placed it in the camera. We wash the plate in a chemical solution, and a real picture almost immediately appears. Suppose for a moment that some one individual had discovered all this on his own account, before Daguerre or Fox Talbot had ever dreamt their first philosophic dreams of recording the image of the camera obscura. Imagine this one ingenious individual calling together a dozen learned men of his time. He explains to them that he can get light to give him a perfect picture at a moment's notice, and he proposes to demonstrate this fact. We picture the 12 philosophers watching the inventor place his prepared plate within the dark box. They examine the prepared plate in the dark room, and are all satisfied that it contains no hidden picture. The very darkness of this room, however, appeals to most of them as a rather suspicious feature. The red illumination is very subdued. Going out of doors, they watch the experimenter arranging his dark box on its stand. Light is to draw the view before them. The onlookers marvel at the audacity of the man, merely lifting off the dark shutter for a single moment. Another examination in the dark room, and all declare that the experiment is a failure. There is not the least sign of any picture. When the inventor explains that the picture is really there, although it is invisible, I can imagine the 12 good men joining in a hearty laugh. The chemical bath into which the inventor proposes to put the pictureless plate is next examined. But there seems no room for any trickery there. With what incredulity would the onlookers watch the plate as the inventor made the chemical solution flow to and fro over it. At last the semblance of a picture does appear. Another chemical bath for the plate, and the inventor hands it to one of the amazed philosophers to take out into the daylight. Truly marvelous, but alas, everything is reversed. Black objects appear white, white objects appear black, and the right and left-hand sides of the picture are transposed. The inventor explains that this reversal, instead of being a disadvantage, is exactly what he desires, for he proposes giving each philosopher a corrected copy of the picture. The inventor produces a large sheet of white paper which he has prepared. He asks any one of the onlookers to cut from this sheet 12 pieces of paper, each equal in size to the glass plate. There can be no trickery here, for if the paper did contain any hidden pictures, they would run a certain risk of being cut through the center. This time, the inventor explains that he will save the gentleman the trouble of leaving the dark room. Having placed the glass picture on the top of one of the pieces of prepared paper, he simply produces a bright flash of light. He then places this apparently pictureless paper in a chemical bath, and very soon a picture appears. Another chemical bath, and the picture is handed to the philosophers, who hasten to examine it by daylight. This picture is true to nature. Black objects appear black, white appears white, the right and left-hand sides are as they should be, and the whole variety of light and shade is perfectly portrayed. Of course, this demonstration never occurred just in the manner here described. I have merely asked the reader to draw upon his imagination in order to impress him with the true romance of photography. It has all happened, but not just so suddenly. Who can fail to be impressed with Daguerre's accidental discovery of the latent image? It reads far more like a fairy tale than real life. There must be few homes today in any civilized country in which photographs are not to be found. In many of our homes, there are hundreds of such pictures. Passing over the sentimental side of the subject, it must be obvious to all that our knowledge has been very greatly extended by such photographs as travelers in distant lands have obtained and brought home. Every traveler is not an artist, but, armed with a camera and photographic plates, he can bring home faithful pictures of all the curious tribes and people he meets. We see the natives' huts, their mode of living, and the strange vegetation. In connection with exploration alone, photography has been of the very greatest interest and service. Instead of killing the painter's art, photography has been of great assistance to the artist, in recording details which it would take too long to draw from nature. Then we benefit by the photographic reproductions of artistic masterpieces. We have seen how it is photography that provides us with the beautiful book illustrations of the present day. We have also seen how the eye of the camera has been able to look farther into the heavens than the human eye can do. Photography has faithfully recorded the presence of stars which man can never hope to see, even with the very best of telescopes. By means of photographs taken through the microscope, the student may examine the invisible germs of disease and learn to recognize the forms of different bacteria. The surgeon photographs the living skeleton and records the daily progress of a troublesome fracture. Indeed, photography enters into the whole realm of science, assisting in a multitude of different ways. Returning for a moment to the pictorial side of the subject, and passing over the marvelous living pictures which photography gives us through the medium of the cinematograph, it is interesting to note that permanent records of important subjects are being stored in the British Museum and elsewhere. The National Photographic Record Association reports that about 4,000 records have been lodged already in the British Museum alone. These should prove of great interest to future generations. As regards the future of photography, he would be a bold man who would prophesy. Color photography has got on to new lines recently, and its future looks more hopeful. It has been now found possible to transmit photographs by means of electricity. Is it possible that someday we may yet be able to see the distant friend as he speaks to us by telephone? It must be admitted by the least enthusiastic that during the last 50 years, photography has done extraordinary things. And may we not hope that still more wonderful achievements will be accomplished by this great invention of the 19th century? End of chapter 23. Read by Anita Hibbard, October 4th, 2022. End of The Romance of Modern Photography by Charles R. Gibson.